Great, thank you, Linus, and thanks everyone for joining us. And I think it's a perfect Arctic day, such a beautiful day with the snow and the sun. If you haven't been outside already, I highly recommend that you do that. So I'll be talking about how ice and ice breakup shape subarctic streams. And I may be promising a lot with this title. I don't have the full answer yet, but I hope to give you some background on the effects of ice in shaping streams. And then I'm going to introduce a new method that we're using that can provide a lot more insight into what happens to streams underneath ice during ice breakup. And then I'll end with talking a little bit about potential climate change effects on these processes. So as a fluvial geomorphologist, which is someone that studies how water and sediment change and movement shape streams and rivers and how that impacts our landscape as a whole, my main research question is looking at what determines channel form and sediment transport processes. So these different pictures, a smorgasbord of different streams, have different shapes. Some are meandering, some are straight, some are very turbulent, some are a little slower flowing water, some have very coarse sediment. And in my world, sediment is everything from clay, silt, sand, gravel, up to boulders, any broken down bedrock. And they change in different frequencies. Some are stable for a long period of time, and some are very dynamic. So the questions are, what is driving this change? And so to start off with, before you gloss over, why should you even care about this? Channel form, well, they look different, and it's kind of fun seeing these out when you're on a hike or looking at photos, but why should you care? Well, if you care about anything else that has to do with rivers, the fluvial geomorphology, so the form and sediment transport processes, they form the template for nearly all other processes occurring in and around rivers. So in terms of ecological processes, everything from habitat quality, quantity, heterogeneity, and ecological disturbance regimes that determine disturbance and mortality for various organisms. The hydrology in terms of attenuating flows and flooding, biogeochemical processes such as nutrient processing and carbon storage, and of course us as a society in terms of sediment transport and erosion affects infrastructure and flooding, and then also a very important area of aesthetic and recreational values. And then we shouldn't just think of a river as this pipe or a channel. The river interacts in various dimensions, as you see in this diagram on the right. The floodplain to the channel back and forth, and further away from the hill slope and upstream and downstream interactions, and vertically from the atmosphere down to the hypereoic zone, which is actually below the channel that still has water and some ecological processes. So us fluvial geomorphologists, traditionally we think of channel form as a product of interactions between sediment and water flows. So this classic diagram, that's a modern version updated from Lane's balance in 1955, shows driving forces on the right side, so how much water and the slope of the channel, versus resisting forces on the left side, which is showing the amount of sediment and how coarse the sediment is. And if a channel is in equilibrium, these driving and resisting forces are in balance. And then we can also think that if we know the amount of water, so Q is water discharge and QS, the sediment flux, and we put those within the filter of the valley geometry, how much room the channel has to migrate, substrate in terms of sediment and vegetation type, then we might be able to get out of it the river geometry, habitat, and disturbance regimes. However, there's a few more factors. Just want to add biotic factors that have been recognized more and more in the past about a decade or two in terms of vegetation that increases bank cohesion. So you can't get a meandering channel, one that curves and is sinuous, without vegetation that stabilizes stream banks. And log jams and beaver dams are really important in creating a multi-threaded complex environment. They form little leaky dams. But is there anything else, especially in our subarctic and Arctic regions? So perhaps ice can also be a driving factor. Now we have ice starting to form in some of our streams and rivers here in northern Sweden, and that can affect the stream in various ways. However, the study area has been a black box in many ways, and it's a black box for 4 to 8 months out of the year when it's covering the ice, and our traditional methods haven't allowed us to really understand the effects of ice on changing channel form. So I'm going to go into a little bit of, first we'll understand the components of a river's ice regime and how these may affect sediment transport or erosion, especially erosion of the stream bank. So we are starting off with in the beginning of the winter season, which freeze up, and the various factors here can affect the capability of sediment transport and stream bank erosion. First, the timing relative to autumn rains and low flows and cold temperatures. And this can affect the type of ice forming, whether it's just surface ice connecting to the stream banks and any boulders or logs in the channel, or whether the channel water becomes super cooled, forming frazzle ice that can then attach to the bed of the channel and form anchor ice. And then we have the ice cover period, and the duration of the ice cover, as well as the thickness and the extent of the ice, can also affect processes underneath the ice. Are there any cracks, or is it completely closed where you're forming like a pipe flow, a closed channel with very high pressures, and how long is this lasting? And then finally, ice breakup, which we often think this is the most exciting dynamic period of the time where ice can really have an effect. So here the timing, again, is very important relative to the spring flood. And then the type of breakup, the mode, whether this is thermal or mechanical, and I'll try what this means more shortly. And then the frequency of ice breakup. So is this occurring just once at the end of the winter period or several times during the winter? And if so, then we may return to this freeze up and ice cover period and then ice breakup. So there's 2 end-member modes of ice breakup types, and then there's lots of combinations of these and a gradient between. On the one hand, we have what's called thermal breakup, which occurs with just in situ melting, so temperatures just increase slowly, and the ice basically just melts it in place. And this does cause a sediment pulse by just releasing trapped sediment in the ice. However, it's usually not responsible for lots of scour. And then on the other side is mechanical breakup. And this is usually due to an increase in upstream flow discharge that causes these ice blocks to crack and then push against each other downstream. This is just from the Ume River, not far from where the Grisbacka, and last winter, like that combination with some beaver chewed sticks here. And then this went further downstream towards town and jammed up against the bridge piers. But here, as you can imagine, this is much more dynamic, and we have potential for much increased erosion and sediment transport for several reasons. One, that the ice is still attached to the stream banks or the channel bed once it is pushed downstream, so it takes everything that it's attached to with it. And you have much thicker pieces of ice that are moving downstream. So with thermal, you can still get ice blocks once they're melting, but they're much thinner and don't have the same capability to erode the stream bank when it's moving downstream. And then because of the increasing discharge, we have rapidly increasing turbulence that has the capability to also erode a lot more and transport sediment on the bed. And then finally, sediment plucking through anchor ice. So if anchor ice formed, and that's attached to all of these perhaps large boulders that can't normally move and can be transported downstream. An example of this last effect shown nicely by one of my collaborators, Lisa Lutsari in Finland. We examined the Tana River in northern Finland. And they scanned the channel bed with something called LiDAR, which is basically a laser scan, and did it before the winter of 2013, so in the autumn of 2012, and then looked at the ice dynamics in the scan again. This is in the middle of September in 2013. And these are the results where the brown orange dots are that from 2012 and the green are from 2013. And what you'll notice is here, this boulder, it's about 50, 60 centimeters large, rotated slightly. Here in the next image, it was moved downstream by about a half a meter. And then this last one in the lower panel actually moved so far down that they couldn't recognize it anymore. And these large boulders aren't capable to be moved by these normal river flows that were measured that summer. And then there's importance of ice, the timing of ice and high flows. So this photo, these are from two different streams, but the one on the left is showing the spring flood. And you'll notice that there's still ice left there on the right stream bank. So that's protecting the stream bank from additional erosion during the big pulse of high floods. And then on the right, this was taken by local Tvärån here in Umeå. And for those of you in Umeå know that we got very heavy rains just a few weeks ago, caused massive flooding in lots of places. And here, if you can see my cursor, this is a newly eroded area here on Tvärån with this very high flood that was higher than our spring snowmelt flood, but without any ice protecting the banks. And this was also shown in a recent study where they examined this closely, and with the spring snowmelt discharge event, this is showing a hydrograph, so the magnitude of the flow on the y-axis and the time on the x-axis. Here, the most frequent changes were on the top of the big flood and the greatest magnitude of changes on the falling limb of the flood. Whereas in a summer discharge event without any ice, then there were much higher, larger changes on the rising limb of the hydrograph. So how can we measure effects of ice in real time? When there's ice-covered conditions and the ice is very stable, and in this case, before we wandered out on the ice, we saw tracks of moose that have walked on the ice, so we thought that was a good sign that it was stable enough to walk on. Then you can actually drill holes in the ice, and through that we have inserted something called an acoustic Doppler current profiler, where we could get very high resolution velocity data on the water. But what do you do when it's very thin ice or during ice breakup? This is an extremely dangerous time to be out on the ice. And for someone like me that does a lot of field work and is out walking in rivers in the summer with waders on, this is not a place where I want to be, and I can't take any direct field measurements. So instead, there is a new technique that I'm going to show you a case study where we have used it, where we can measure from a safer distance what is happening underneath the ice and during ice breakup. And this is using seismic monitoring. And most of you are probably aware of seismic monitoring. It can detect earthquakes and describe the intensity, magnitude of earthquakes. And so I'm going to show you several of these diagrams, and we're going to focus mostly on the spectrogram here on the right. And what it's showing is time on the x-axis, the frequency in hertz of the signal on the y-axis, and the intensity of the signal is shown by the warmness of the color here. So the more red, the more intense the signal is. And you see the earthquake starts very suddenly and then it drops off fairly quickly as well. But you can measure lots of other signals other than earthquakes. For example, an anthropogenic noise, and in this case, it's a truck driving by. So here it increases slowly and then decreases in intensity and at the same rate. But then even more exciting than that is that we can measure lots of geomorphic processes. So that's what's happening on the landscape and is changing the way the Earth looks like on the surface. So there's several processes such as a rock slide. So there's just rocks tumbling down. These are from studies in the Alps, so very dynamic environments. And so here you can kind of see it's a little stochastic, lots of different movements here. And debris flow, so that's a lot more sediment moving down a hill slope together in kind of a more a viscous flow. And here we see a different type of signal than the rock slide. And finally, bed load, that's when sediment is moving along the bed of a river. And all of these different types of signals have different seismic signatures in terms of the frequency and intensity, if you're the same closeness, proximity to the signal, and then also the way they look like, how fast it starts and how it drops off. So we applied this in a case study in Sävarån, which is a river about 60 kilometers northwest of Umeå. I'm going to go through methods and some of the results in a paper we just published this summer in the journal Geophysical Research Earth Surface. And this is what this river looked like in March of 2018 when we started our study. And the objectives of the study were to, one, just to examine the changes in hydraulics and bedload sediment transport in a subarctic river using a seismic network. Can we just see these seasonal changes? And then to provide an estimation of sediment flux in an ice-covered river up in Fennoscandia, because that has never been done before during ice-covered conditions. And being able to show that there's a proof of concept that we can use seismic measurements for ice-covered conditions, and especially during ice breakup. And even more specifically, we're comparing these seismic signatures of hydraulics and bedload sediment transport and how that differs during open versus closed channel flow. And whether we can detect a seismic signature of the ice breakup, and does this differ if it's mechanical ice breakup or thermal ice breakup? And then if we can even see some distinct patterns of fluvial processes, for example, at really high temporal resolutions at the diurnal scale, that's really hard to measure even without ice-covered conditions. So our setup looked like this. This was our reach, the segment of river that we were interested in. And this black line shows a transect where we looked at stream velocities more closely. I'll show you in the next slide. And so within about 40 to 80 meters, we inserted 3 so-called geophones that are passive seismometers and a broadband seismometer a little further upstream. And these, as you see, they're fist-size devices, and we dig them out. So it was March, there was lots of snow. We had to dig out the snow, and then about 30 to 50 centimeters below the soil surface. And it's attached to basically a car battery and a logger that logs all our data. We also had 2 time-lapse cameras, so we could independently verify the ice cover and ice breakup. And we created a simple tree gauge. So gauge is what measures the height of the water by just taping markings on a very straight birch tree right on the edge of the channel. And we had pictures of this from one of the cameras. There's also SMHI, the Swedish Meteorological and Hydrological Institute, has a gauge 8 kilometers upstream, so we could get independently verified discharge data, and as well as 2 weather stations in about 50 kilometers away in 2 directions, where we could see how temperatures and wind changed throughout our measurement period. To get independently verified velocity data, we drilled 11 holes along a transect about 1.5 meters apart, and we inserted this ADCP, that's a acoustic Doppler current profiler that measures the velocity profile from the surface of the water down to the channel bed. We'll take a look at some of the results from this velocity data right away, which we compared with summer data, and we came back and here, luckily we don't have to drill holes, but we sat in a little rubber boat and found the exact locations of those drill holes and took data in those same locations. And during the winter time and the summertime, we took 5 minutes of continuous data at each of these hole locations. And so these are the summer data from June, and the top numbers are the time averaged surface velocities, time average bottom velocities underneath. The black points are the locations of the maximum time average velocities, and below are the maximum instantaneous velocities. So there's a lot of data here we've shown. But basically, this is an average velocity profile of a stream. There's nothing too exciting here, but what you see is that the highest velocities are closest to the surface, which makes sense. There's not a lot of friction there. If we compare it to wintertime velocity profiles, here right away we see a few differences. But one is that the highest velocities in winter are not at the top, they're in the middle of the water column. Obviously here there's friction from the ice at the top. And then what I think, and then the Thalweg, which is the area where we have the highest velocities in the deepest part of the channel usually, that changes position from here on the right side of the channel to more of the middle of the channel. But one thing that's quite interesting is that the discharge was lower in the wintertime. So therefore it makes sense that we have lower overall velocities in the wintertime. However, the highest instantaneous velocities were also recorded in the wintertime. So in the winter, there's much more heterogeneous flow, there's pulses of water, and so the places where erosion occurs may differ in the wintertime than the summer. So let's take a look at this fun, exciting seismic data as I see it. And we'll start off with just interpreting the 48 hours of data so you can get to know what these spectrograms are showing. And so here on the x-axis we have Julian days and then hours. So this is 10 p.m. at night and 8 a.m. the next morning. And what you see first with just a few hertz signal, we see a little band down here with a few spikes. And this is actually recording ocean noise and distant earthquakes. We see this kind of very noisy signal up top and very broad band of frequencies for about a day. And this was a very windy day. And so this is wind in the trees that's contributing noise. And then down here, there's a constant band right around 10 hertz. And that's corresponding to the river turbulences. So this is actually picking up what is happening in the stream. And then you'll notice that there's a big red spike here in the data in terms of frequency and the intensity of the noise. And so we were here the day before and then the day after. And what we saw the first day, it was completely snow covered with a small little opening here further downstream. And then the next day, the opening was much larger and there was a big crack in close to our transect with velocities. So we interpret that this is a signal of ice cracking. So this was just 48 hours. Now let's take a look at the whole season of data. So this is starting from early March and we're going until the middle of June here. And what we have here is right around here, these photographs are kind of showing where they are occurring. Around April 25th, 26th, right around here is when ice breakup occurs. And then we have the highest flows right here in the middle. This was a very big summer storm around June 6th. It was very windy and rainy. So we have this 10 hertz turbulence signal that's continuing through the winter and then increasing in intensity during the high flows. And then showing up a few days before the ice breakup is a signal around 30 to 50 hertz. And this corresponds to sediment transport. So what's happening at the bottom of the bed, we have sand, gravel, and cobbles moving downstream. And another thing I want to point out, which I think is quite exciting, is we see these little humps in the data. And these are corresponding to diurnal changes. So we're seeing changes in the sediment transport within one day. So if you think around the snow melt period, then snow is freezing during the nighttime and then melting more during the daytime. So we have this pulse in flows, and we also have a corresponding pulse then in sediment transport. And this is super exciting because this is very hard to measure with such a high temporal resolution and continuous data in any other way. And what else can we get from this? So this was a spectrogram that I showed you. And then I'm not going to go through the steps that we use to do this, but there are physical models, physics-based models that can predict the seismic energy based on water flows and sediment transport. And then my collaborators, Misha Dietz, has created a inverse model to be able to take the seismic energy and with some other independent data from a site to be able to back calculate how much sediment flux and the water stage or the height of the water at every minute time slice. So from that, we were able to get a curve down here, which is a bedload flux, so how much sediment is moving throughout the system. And we were able to calculate a cumulative sediment flux of 56.2 tons per square kilometer. And we claim that this is a close to per year number, since this is the most dynamic period of the year. And where about 5% occurred before open channel conditions, so underneath the ice, which isn't a large number, but is still not completely insignificant. And we're also able to calculate catchment-wide erosion rate, which is an order of magnitude less than the Alps, which is not surprising from previous maps. I don't expect you to interpret these, but just want to show you that there's been very, very coarse estimations of the sediment yield in these areas. So this map estimates that northern Sweden has sediment yield of 0 to 5 tons per square kilometer, whereas this one we're in category 0 to 50. So here, with this method, we're better able to constrain the overall sediment flux, so how much sediment is eroding from our hill slopes, our landscapes, and moving downstream out of the system. Another thing we can do with these data is analyze ice cracks. And from the timing of the ice cracks, we can infer ice breakup mechanisms, whether it's mechanical or thermal. So if it's mechanical, we would expect to see a sharp increase in the number of ice cracks right around the ice breakup time, and then it'll subside after ice breakup. Whereas if it's thermal, there'll still be some ice cracking, but there shouldn't be a big spike right before the ice breakup. So we can detect and locate discrete seismic activity, where their ice cracks are sudden, short, impulsive signals. And we can pick that from a stream of data by looking at kind of the running average of the short-term average versus a long-term average of the signals, and seeing when this short-term average deviates a lot from the long-term average. And we were able to pick out these signals, and if you have at least 3 geophones, you're able to even locate where they occur in space. And this is an aerial photo where you can see the black is the stream reach, and there is a road about 100, 150 meters away. But you notice that our signals are mostly occurring within the channel, and there are some signals picked up here where there's a bridge, but there's a much more turbulent section here with a lot more large boulders. But so hopefully you guys will buy this, that the ice cracking signals are coming from the river and not elsewhere. And so here's the timing of the ice cracking. This is from, again, the end of March until the beginning of May. And you'll see right around the ice breakup, then the ice cracking completely disappears, which makes sense. There's no more ice. But we interpret this as evidence for thermal breakup. There wasn't a huge spike in ice cracking, but with some elements of mechanical breakup as well. And that was confirmed by our photos. And as an interesting side note, you'll see that the density, the timing of the ice cracking was mostly in the early afternoon. And so let's look a little bit towards the future. So river ice regimes have and will change with climate change. There is a nice paper that came out in just the beginning of this year, where they mapped the global river ice extent using Landsat satellite images. And so this is the river ice extent in about the past, it was 10, 15 years. And so up here, not surprisingly, we are between 75 and 100% river ice extent. But they also looked at the changes from 1984 to 94 compared with 2008 and 18. We're already seeing a decrease in ice cover. We are around 5 to 15% decrease up in our region here. And then they also model changes, expected changes between the 2010s and 20s compare of what is a river ice duration in various areas in the Arctic and subarctic, where we are currently at about 3 to 6 months up here in our part of the world, whereas at 2080 and 2100, then this will decrease, where this intermittent and with just a few months will move northwards. So thinking about this and what we talked about already, I just want to leave you my last slides here and some hypothesized effects of climate change on the ice regime. So with just a small change in climate change, kind of like what we noticed last winter, we have more freeze-thaw events and going back and forth around 0 degrees Celsius. So more freezing and thawing. The ice duration and cover will decrease, but the amount of 0 degree Celsius crossings will increase. And this may lead to more thermal breakup or perhaps more mechanical breakup if there's a sudden temperature change. And so with less ice cover, we expect more winter erosion, but perhaps less severe ice erosion during the breakup period. And then if we have very large effects of climate change, that mean that we have barely any ice cover and very low duration, that we stay completely above freezing, then the winter erosion is expected to increase. And however, the ice breakup erosion will decrease even more. So it really depends on the timing of these high flows and whether we'll see more thermal or mechanical ice breakup. So to conclude, I think I've shown you some evidence that ice regime can be a driving factor in shaping subarctic streams, but there's many questions that remain. For example, how large is the difference in sediment flux with a change in ice cover and with mechanical versus thermal breakup? And whether the ice cover and ice breakup significantly affect long-term channel geometry. Are these streams at northern latitudes inherently different because they're covered by ice than other streams? And which types of streams and rivers are more affected by changes in ice regimes? And will this decrease in ice cover have an overall positive or negative effect on stream bank erosion? So I don't have all the answers, but I do think seismic data can help us unlock these answers and help us prepare for a future. So thank you for your attention, and I thank my collaborators, especially in the study on Sävarån.
Okay, thank you very much, Lina, for that very interesting presentation. It was all news to me, but I'm no natural scientist, so it's very interesting to hear. And I leave the floor open for questions. Steve, did you have a question, or did you just applaud?
Thank you.
I can't hear you.
Sorry.
Oh, that's
Hello, thank you for your talk. It was nice. I work with the ocean, so I'm a bit further downstream.
Exactly.
And I was wondering if this would be possible to use also in the coast, or is the signal too high?
You mean the seismic data?
Yeah.
Yes, I mean, you would absolutely pick up ice cracking and those days. So I haven't used it in the coast, but as I said, there's this ambient noise that you pick up at any time. So, I mean, it's really just a matter of getting to know the seismic signatures of different processes and being able to verify it with some type of independent data so that you know what you are looking at. Yeah, so absolutely, I don't see why not. It's just a matter of finding the right places. When we picked the study site, we were looking for a place. Partially that winter, we wanted to be able to be on the ice, of the stable ice conditions, but also that was easily accessible. I had to go out every month and change car batteries and download data. And it was easily accessible, but at the same time, far enough from traffic so you don't get a lot of extra ambient noise that covers up the signal that you're interested in. So it's a matter of finding those places that you can get enough data, but not the data that you don't want.
Thank you.
I can say, add to that, I've had, together with my collaborators, we've thought that maybe it'd be worth analyzing some more broader scale seismic data because there's big seismic networks throughout every country. There's we're monitoring large scale events, but seeing can we pick up maybe when Östersjön breaks up or freezes, or can we see differences from that, from these large scale seismic networks?
All right, then Gudrun Norstedt has a question.
Yes, I wondered about these differences in thermal and mechanical ice break. Are different locations more or less prone to have a thermal or a mechanical ice break? Different river stretches, I mean.
Yes, absolutely. It hasn't been analyzed in depth, but I mean, one thing is that if you have a northward flowing river, then that's a very large river. Then that's the upstream reaches will melt earlier. So then you'll have an increase in flow earlier and be traveling northward, which is downstream. Then you're more likely to get mechanical breakup there than a thermal breakup. And then
if you look at different stretches of Sävaron, for example, is it possible to predict what stretches would be more prone to mechanical breakup or thermal breakup?
Just by their morphology, how they look.
Yeah, if they're rapids or
yeah.
or more calmly flowing waters, or.
Yeah, I haven't thought about it in depth, but I think there must be some factor. So if you have a lake upstream, then you're less likely to get a lot of ice cover because there's more warmer water being pulled there. And I would suspect if you have a more turbulent, I think it matters more what is just upstream, if you're able to melt that earlier, so you can have increasing flows and discharges before you're melting something thermally. So I would say in many cases that like a slow flowing CL, for example, would be more prone to thermal breakup, whereas rapids would be more mechanical. But don't quote me on that. I hope to do more studies on that and we can get back there.
Thanks.
Okay, thank you. Then Jasper Kandel has a question.
Hello, my name is Jasper Kandel from Wageningen University in the Netherlands.
Okay, welcome.
Nice, thanks to the online world, we can now see nice talks from a far distance, and it was very interesting, so thanks a lot. And I was wondering, so you raised the question whether ice has actually an effect on river channels on the long term. Well, do you think it has? So do you actually get different channel patterns because of the presence of ice, or is it mostly the channel morphology itself, or also really the pattern of the river?
Yeah, so this is just speculation on my part, but there's a few thoughts I have. One, if you have ice protecting the stream banks, during high flows, then you're less likely to get lateral erosion and more likely to get incision. And so maybe you'll have lower width to depth ratios. So narrower channels overall in places where there's ice covering the stream banks is one possibility. In other places, I've actually heard anecdotally, in places where there is a lot of mechanical ice breakup, so you have all this ice jamming, then you are getting a lot of increased stream bank erosion, and then you get preferentially wider channels that way. So those are kind of pointing in two different directions. But
now actually the effect of ice is moving more northwards. Shouldn't we study those rivers that are actually changing from fully ice covered to, well, non-ice covered? So maybe this is the moment.
Yes, exactly. I have, yes, projects in mind and grant proposals submitted where I'd like to look at gradient from Abisko in northern Sweden to further down in Sweden and look at these changes in the stream bank processes with the ice and maybe different ice regimes and further north and what will happen with climate change. So
nice, interesting. Thanks.
Yeah, absolutely. Hopefully I can tell you more in a few years. We'll see.
Yeah, would be nice.
Yeah, thanks.
All right, thank you for that. Then we don't have any more questions right now. Anyone want to say anything? You're very welcome. Okay, Gudrun Norstedt has another question.
Just another question. You said something about, I think it was the thermal ice break, that there would be a pulse of formerly trapped sediment. Was that right? In what way was the sediment trapped before the ice break?
Yeah, I mean, if there is actually, this has been, I read that in the literature that has that if you have a trapped sediment, I mean, if it's if something is when it is the freeze up, then if there's suspended sediment in the channel, then it's freezing in the ice, and then it can be released all at the same time. But on the other hand, that said, when I have examined some of the ice, especially here Sävarån, then when ice is freezing, then it's expelling all this other organic material, so DOC, dissolved organic carbon and such. And so the first freezing is very, very clear ice. So I'm not sure how common it is that there's a lot of extra sediment trapped in thermal. But regardless, it's a much lower effect than with mechanical ice breakup, but that is the one potential effect of it, increase the sediment pulse just during the ice breakup.
Would it depend on the relation between the thickness of the ice and the size of the channel? If there's a lot of ice compared to the water flow, there would be more sediment trapped in the ice. Or?
Yes, exactly. I can imagine that. Absolutely. So, and if there's any anchor ice forming, then that's can possibly trap more sediment in there. Absolutely.
Very interesting.
Good questions, making me think. I like it.